Oh, yes.
So it's my pleasure to welcome Alexandre Trilles from the Jagiellonian University. We speak about characterizing, which we want to measure flow via the FK-pseudometric.
Thank you for the opportunity to talk, to present part of my research. And as mentioned, the goal today is to characterize mostly Kronecker measures for continuous flows using the FK that stands for Feldman-Katok pseudometric. And yeah, okay. So this may be something new to some of you. So let me start by explaining what this all means. So first, let me say what I mean by a continuous flow. So the whole time xt is going to be a compact metric space. And a flow is simply an arc action space that can be represented by this function that takes t in a point here and it has to publish. So this function we can look to the Borel sigma algebra induced in this space, considering the product topology. If this function is measurable, we're going to say that this is a measurable flow. If it is continuous, then it's a continuous flow. So pretty simple. And of course, we need also that F0 is the same as the identity, and as Ft plus X the same as Ft by X. All right. Well, if we fix one real number, then we have a homomorphism or isomorphism in the space, which is a map. So we sometimes denote this in this way by the maps. And this is called the time t map. So if instead of fixing the time, we fix the point and run across R, then we look to the orbit of X. And it may happen that this is a single point. So it may happen that the point is fixed, which is called a singularity. And today, we don't have singularities. So we're talking about non-singular flows. Okay, so we know where is a continuous flow. About measures, I mean in the sense of ergodic theory. So Borel probability measures on this space. I'm denoting this way the invariant measures. Which means that phi t of A is the same as the method of A.
Only finite measures, or do you allow
Borel probability measures.
Borel probability?
Yeah, Borel probability measures. And we have the ergodic measures. Which means that if stack is invariant, then this is either zero or one. It's either a null set or a full measure set. So our system is indecomposable. Okay. Okay. So if we have an invariant measure, so we can look to the triple as mu. Here we assume that mu is an invariant measure. So this is a measure preserving flow. And if the measure is ergodic, then we just say that this is an ergodic flow. For this, of course, we don't need to have continuity of the map. But if the flow is continuous, then we know that this space is not empty. And of course, the ergodic measures are also not empty. Those are the extremal points of this space. So this is just to say that we can look at a case where this is a continuous flow. Yes. Okay. So we already know what's a measure preserving flow. The notation, I think, it's more or less clear. And then we go to something that may be now the new thing, which is what is a loosely chronic. So if you are familiar with loosely Bernoulli flows, this is the same as being loosely Bernoulli. Plus having zero. So the story is more or less, so when Ornstein was studying the isomorphism problem, he showed that shifts with the same entropy, they would be equivalent. He defined a notion of very weak Bernoulli partitions using the D-bar metric, pseudometric for shifts. And then Feldman changed a little bit the D-bar to F-bar, defined the notion of loosely Bernoulli partition. And consequently, if all the partitions were loosely Bernoulli, he called the system as the automorphism. That was a measure preserving transformation, loosely Bernoulli. Well, Bernoulli is usually associated to positive entropy, but it turned out that loosely Bernoulli could have zero entropy, which was very strange. And then at some point, they thought that all of them would have zero entropy. It turned out that this was false. So a lot of theories came out from this. And why we call this loosely Kronecker? This is because it was shown that if a system, a measure preserving system, either continuous or discrete time, is loosely Bernoulli and has zero entropy, then this is Kaplan equivalent to a Kronecker system, whatever it means, if you don't know what I'm saying. And then because of that, Ratner suggested that we could call this loosely Kronecker. So we're going to say that two measure preserving flows, not necessarily continuous here, they are isomorphic if there exists an isomorphism. This space to space preserving measure such that
basically all the loosely Bernoulli plus positive entropy is Kaplan equivalent to Bernoulli. So is this loosely really the same?
Yeah.
So that's very nice.
Yeah. Yes. Okay, so this is coming from that. Sorry, there's someone calling. Okay, so this is class
You don't mean the other order for study?
No, we're fine. Oh, yes, yes, of course, of course. For MT and mu almost. So this is the notion of isomorphism, which is quite strong for flows, because for flows usually we like to use the time changes. And for instance, if instead of isomorphism we ask for a homeomorphism, so topological conjugacy between these two flows, this is extremely strong. And even if we just change a little bit the speed in part of the flow, it's not topologically conjugate to itself. And then people look to orbit equivalence. And here we look to something similar when we talk about Frankfurtian equivalence. And then we're going to say that these two guys, there are two measure preserving flows, they are Frankfurtian equivalent if there exists if the first one is isomorphic to, I'm going to this way as time change of the other. And this time change is not varying too much. So, well, they're going to be Frankfurtian equivalent if one is isomorphic to the time change of the other. So for flows, this is way more natural, right? Okay. And then we come to the actual definition. For now, it's more like notation and recalling some notions. We say that a measure preserving flow is the Kronecker. If it is Frankfurtian equivalent to suspension over an invariant rotation. So a system is Kronecker, it's called Kronecker. If it is Frankfurtian flow, it's called Kronecker if it's Frankfurtian equivalent, just suspension over an invariant rotation. So it's a very simple system. And flow is going to be loosely Kronecker. The measure preserving flow is going to be loosely Kronecker if it is Frankfurtian equivalent to a Kronecker system, right? And then, well, this definition at first is for the measure preserving flow. But as I said, we're going to be focused on continuous flow and a measure which is invariant for this guy. So we're going to say that the measure is loosely Kronecker if an invariant measure is loosely Kronecker when the resulting system is loosely Kronecker. So, okay. So now we know more or less what is this. Okay, so most of the study of loosely Kronecker flows was done in the context of looking to discrete time systems derived from flow, cross sections, time T maps, things like that. Most of the things were like that. One example, possible example of loosely Kronecker flow is the Hortal cycle flow on the surface, a complex surface of constant negative curvature, expressed by Ratner. Also using some sort of discrete time systems. But then later, Ratner actually studied these guys from the continuous time perspective, providing a criterion to identify if a system is loosely Kronecker or not. And so let me just recall her characterization or criterion. So, of course, she's gonna look to partitions. So I will denote this way the set of finite partitions. Finite mappable partitions. And yes, so we say that X, let me fix X and Y and space at time T and a partition in this space. And say that X and T, X and Y are and X 0 T epsilon T natural if there exists H here, so that's equal to T and absolutely continuous function. Increasing, strictly increasing. Such that. So these two sets, we want them to be big. So this is the Ladite measure. So we want both these sets to be large in proportion to the whole interval T.
May I, excuse me that I'm going back just to clarify the definition. So because we have this time change, does that mean we can always assume without loss of generality that the whole function is one?
Yeah, because exactly, this is the thing. When I say suspension here, at first I'm talking about the sign one, but it could be any special flow because one is the time change of the other, so they're going to be kind of equivalent in a way.
Some people understand suspension
as
a general.
Yeah, it doesn't really matter now because we look at the time change. Since we're considering time changes, then this is the same. It doesn't really matter. So they're going to be T epsilon P matchable if there exists a pair of sets contained in 0 T interval, and also a continuous function H from A to A prime, which is increasing, such that, well, those guys are big. Being absolutely continuous is just to guarantee that the derivative exists mu almost everywhere. And we want this derivative to be close to 1, epsilon close to 1. So we are allowing some changes, time changer, but not a lot of information. And the third thing is that we want that this guy here is in the same element of the partition as this guy. Yeah. So let me draw a picture. So we have the orbit segment of X. X is coming here to here. We have, let's say, Y is starting here, go somewhere, get close here. So, Y is going much faster because, well, if you can see, like, it's longer for the same proportional time. And then eventually we would have, let's say here, T, we could have someone here, here, like this all one. Could have then what's happening here is that we're looking to this part of this orbit segment, this part here, 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 for example. And what this is saying is that we have a point here, and these guys, they are in the same element of the partition.
So do you assume anything about A and A prime? In terms
Just
of
measurable.
Just measurable.
Just measurable.
Okay.
But then eventually we can look at open sets by changing some of the things. And the proportion is actually large. We can pretend that this is actually big.
But what is the quantifier over S in 2 and 3?
This is for every S. Okay, this would be for new almost every S in A, but then we can just replace this A and can assume that this goes for every S here. Okay. And she used these to define, to study some sort of entropy-like stuffs. And then what she was doing is that she defined F T X Y P as the gap, which is infinite of axons, such that X and Y are T X match. And then we could, of course, define kind of ball, which are the points in the space such that this is less than X. Okay, so it's almost like a ball with respect to this notion of matching. This is looking how big we can find a matching between these guys so that the corresponding points here are in the same element of the partition. So essentially, to change a little bit the time between these orbit segments and looking to guys that are more or less same size and big. So here's not really well represented. It could be like here, and something bigger here. So in proportion, we have big proportion of this orbit segment in terms of the time that they are going are matched by being the same element of the partition. And this is almost like a way of measuring distance between points. Is that clear? And then, well, if we have this notion which is similar to balls, we can look to one denoted this way, which is the smallest amount of, let me call this TX and P balls. Took over 1 minus epsilon in terms of the measure of the space. So we have the space X. So essentially what we want is that we're gonna have X1 up to Xn, and the measure of the union of the balls, guys, I know that this is bigger than 1 minus X.
But wait a second. It seems that you are claiming, FK is pseudometric?
It is not. This is almost like pseudometric.
Okay.
Yeah, it turns out since we have these parameterizations, well, you could have zero distance. No, you could not have zero distance between different points. But here, if we have y and z in the VT x absolutely ball, then these guys, they're gonna be, I think, 5. The triangle inequality doesn't hold because we have these errors. I think it's 5 times the initial one. Let me just check here so I don't say something wrong. Yeah, so it's almost like a triangle inequality. If the two guys are in the same ball epsilon, we need to enlarge a little bit because of the matches. So, it's almost a metric actually, right? So 2 points are going to have distance 0 if and only if they are the same, because we need to have the whole space. It's symmetric for sure because we are talking about morphism, so the measure, the back measure. But if the two guys are in the ball, then they are close to a constant. Instead of 2 epsilon, right? Here would be like from y to x to z would be like 2 epsilon, but then we have this extra error factor that goes to 5 epsilon. Okay.
I guess the question is why would you expect K to be finite? Or when you expect it?
Because it contains looping balls, right? If we have a point here, let's say that we have another point here which is sufficiently close, then if it's sufficiently close, then the orbit of this guy should be following this one. And we are talking to okay. Yes. Based on the things that I'm gonna say in terms of I cast this partition to something which is actually in terms of the distance. Then we can look to partitions that are almost open, and then this is gonna be a finite cover. And we can look to the different set. So yeah, it could be infinite. This is not a big problem. But let's assume that this could be infinite. This is not a problem for now. For the characterization, this is not a problem. Okay. Because as I said, she wants to look to something which is similar to some entropy. So she finds the beta. What's the notation? Let me just check here. So beta. B. Okay. That's B. So here, alpha. Let me call you all non-decreasing. Onto functions alpha from R plus to R plus. Okay, so we're just looking to almost increasing functions, not decreasing, but onto and alpha. I'm taking one alpha there, so we can look to the linking. When t goes to infinity of log of this k t that's like t over alpha t. So this is almost like an entropy, but we're evaluating in all possible kinds of speed, not necessarily t.
Beta of alpha?
Yeah,
Okay.
with alpha being one of those functions.
One more question, I think related to the previous discussion. So it might be that the function ft for some given xy is infinite, right? In the sense that the set over which you take is empty if you cannot match for any epsilon, or is there?
Well,
or is
if
it so?
we're in a compact metric space, so we can assume that the diameter of the space is 1, and
Sorry,
then that the diameter of the space is
the
1,
diameter, okay.
and then they are going to be T1 P matchable.
Okay.
Not P. Okay, you're yeah, okay. In terms of the measure, this could be okay, they could not have a good match. Yeah, we can just set this as 1. Okay, we can set this.
Wait, if we take epsilon is 1, then
Yeah, no.
epsilon.
Yeah. Yeah, no, I was messing up with the thing that I'm gonna say later. So we can say that this is 1 if there exists no match. So we can assume that they are sufficiently far. As you were saying, if it was 1, then we would not have these sets. So it's like looking at the limit.
Okay.
So this is a kind of entropy-like formula, but with different kind of speeds. And what she said, what she proved. Okay, so first, just a bit more of notation from her work. So define beta. So we can define the entropy of alpha as it leads to max 0 of beta of this partition. Okay. Well, if you reduce the epsilon, then this quantity is increasing, right? Yeah, if we have epsilon, we need more holes. So it's not decreasing. We look to the lim sup of it. And finally, last thing, the sup over all partitions. Fine. Why I'm saying all this? Because in her work, she proved that measure mu is exclusive Kronecker. If E 0 for ML. So what this is saying is that those systems, they are very, 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 very stable, right? They not only have 0 entropy, but they have, with respect to this stronger kind of way of measuring distance in some sense. It's always that the entropy is always going to be 0. Yeah. Okay. So I already talked about what is continuous flows, measures, exclusively Kronecker measures. I gave this criterion that Ratner proved to identify with Kronecker measures. but I'm not talking about Feldman-Katok yet. I didn't talk about it yet. So let's move into that. So for now, I'm gonna think about the discrete time case.
So,
Okay, you probably said question. Okay.
I just wanted to ask, this is for continuous flows?
Yeah, it actually goes for measure preserving flows, not necessarily continuous.
So it's general measure theory.
Yeah.
Okay, okay.
I was trying to think about the proof of this result. Is it maybe possible that the direction where you start with the Kronecker is easier? Both are hard. I mean, I was trying to, on one sense, when you have this suspension flow, I guess it's not so hard to imagine the matching, but I don't really understand where does the assumption that it's a irrational flow on the base comes into.
Yeah, in her case, she was working with the standard definition of loosely Bernoulli. The standard definition based on the partitions that I didn't define here.
Oh, I see that.
Yeah, because the loosely Bernoulli systems, they were defined via partitions. So as I was saying, Feldman defined, inspired in the very big Bernoulli notion of partitions, he defined the loosely Bernoulli partitions, and he defined that the system would be loosely Bernoulli if and only if every partition was loosely Bernoulli. I didn't define these things. And then later they realized that this is the same as being Kakotan equivalent to irrational rotations. And then she was working with the original formulation in terms of the partition to prove this result. Okay. All right, so let's move into the Feldman-Katok pseudometric finally. First, I'm going to talk about the discrete time version of it that was defined by Feldman-Katok and Ratner in 2016. So this is going to be a topological dynamical system for me. It's just a continuous map on a compact metric space. And the notion of matching, so I'm going to say that phi is n delta matching. So here, the n is an integer, and delta greater than 0. If this is defined as from D to prime is an increasing bijection. Increasing bijection. Such that okay, yeah, these two guys here are contained in 0 and -1. And this is going to be a matching between x and y if the distance between ti of x and t pi of y is less than delta. So this is somehow similar to what she was doing there, but in a discrete time version, and instead of looking to partitions, looking at the points being sufficiently close. And then we can define the n delta gap between the points.
But wait, what do we know about the density of P and P prime?
We don't know it. We don't know so far. We just know that this is going to be an n delta matching. If these two guys they have the same cardinality, this function is an increasing bijection. These two guys are contained in 0 to n minus 1. And the corresponding guys, they are delta close. So what we have is that we have x, this is the property of x, we have x, this is x, and x. And then we have y that will be here, then t of y here, close, then t2 will be far, and maybe t 3 could be here. Close. So we don't need to have the same iterates, but we need to preserve the order. So it's an increasing bijection. So we have preserved the order. And this is good because if n is large enough, if you're familiar with the ergodic theory, then we can think about the empirical measures. So those are 1 per n beta measure on the point. So those are the empirical measures that somehow generate some measures. The measure is ergodic, you almost every point. This measure is going to converge to the measure. So we can think about this. So we can think about this empirical measures. And if these two guys, they are sufficiently close for many guys here, then the empirical measures, they will be somehow close in the weak topology. So, okay. So I think the picture is more or less clear now because they look at the end of the gap. And what's the end of the gap? End of the gap is 1 minus the best possible matching that we can have, that I would denote this way, over n. So consider the best possible matching, n delta matching between these 2 points. It's how much I can cover. So the guys are going to be sufficient, they will be very close if we can match great part of the orbit segments that we are looking at. Then the closer they are, the smaller is the gap. So this is why they call this gap. And of course, in dynamics, we want to look to asymptotic behavior. So we can look to the lead tube of F and delta between these two gaps. So what is interesting here is that if 2 points are in the same orbit, then they will have 0 distance. Because we just ignore part of this orbit segment, and the greater we go, the greater is the n, the gap is always this initial segment, so we're not losing anything. And then the Feldman-Katok pseudometric Feldman-Katok pseudometric is the increment of the deltas such that this is less than that. So it's the increment for which the n delta gaps for a very large n, they are very small. Right? So these have some nice properties. If one point is generic for a measure and another point has 0 distance, then this other point will be also generic. For if those guys here, if the Feldman-Katok distance is small, then we look to all possible invariant measures that are accumulated by X, non-possible measures accumulated by the empirical measures of Y. These sets, they will be how to close in the weak topology. So they have some nice properties. There are some notions of convergence where we can talk about entropy and how the entropy function is lower sum continuous with respect to this weird kind of thing. But this pseudometric it's called Feldman-Katok because it's inspired in the F-bar pseudometric for symbolic systems that was studied by Feldman and by Katok independently in the 70s, which is the core of loosely Bernoulli systems. And then, so yeah, well, this is why they call it the Feldman-Katok pseudometric that I usually make it fun. Pseudometric. And it was used originally to identify some loosely Kronecker measures and consequently answer an open problem about whether some measures constructed in partially hyperbolic diffeomorphisms, they would have 0 entropy or not. So it was some sort of construction, and then they showed some nice ways of identifying if we can find a good sequence of points that are generic for the measures with a nice behavior in terms of the Feldman-Katok, then the limit measure is loosely Kronecker. In particular, it's going to have zero entropy, and this is how they answer the question, but this is not the focus today, because later.
So this is this collapse you are trying to
yes. Yeah, it's the JIKN
yes.
Construction.
And so, yeah, and one more question. When you say pseudometric, it simply means a metric which does not necessarily distinct points, or
yes.
Yeah.
Yes. And then later, there was a theorem of Felipe García-Ramos and Feldman-Katok, where they proved that XT was an dynamical system. Use an ergodic measure, and mu is loosely Kronecker if and only if there exists a set of full measure such that we cannot distinguish points inside the set. So the diameter of the space with respect to this measure is essentially zero. So there's a full measure set for which we cannot distinguish these points with respect to this Feldman-Katok pseudometric.
Mu is what's written there? Then mu is
loosely Kronecker. Sure. Just I was like in some space. For the notion in terms of the discrete-time systems. And one of my goals was to extend this result to flows. But at first, we don't have a notion of the Feldman-Katok pseudometric for flows. So, as I said, this notion here of matching, this is somehow similar to the notion of matching that we have for discrete-time systems. So, what we can do is we can say that they are T epsilon delta matchable if we have this whole situation. But here, instead of looking to be in the same partition, I want the distance between IS of X and phi HS Y to be delta. And then now we have a good notion of matching. Now that I have,
sorry, in the discrete case, the loosely Kronecker, what's that analogy?
Yes, it is. It is proved because, yeah, well, being in Kronecker system is the same as being equivalent, isomorphic to translation and a compatibility group with the hard measure, which is Kronecker, and then it's the same via Kakutan equivalence kind of things.
Okay.
So it's the same, essentially the same notion. Okay. And in fact, yeah, if we think here, yeah, every suspension over a loosely Kronecker flow system transformation is going to be a loosely Kronecker flow. So yeah, they are connected via, because this notion of the of partition is defined originally for discrete time systems, and then when they go to flows, they look at cross sections or special flows, because every flow, every measure-preserving flow is isomorphic to a special flow, a suspension with not necessarily a root function being one. Mm-hmm. And then, yeah, the Kakutan equivalence is the same. So it's in more or less the same idea, essentially the same idea. And then now we have a good notion of matching. So since we have a good notion of matching, we can talk about similar things as we did before. Similarly to what we had in the discrete time case, we defined the T delta gap here. So we can find the T delta gap between the points as, let me put this to say that this is the flow. This is the infimum of the epsilons such that X and Y are E epsilon delta imaginary.
It's just continuing the question of Adam in the discrete case, because you mentioned the Kronecker system, but because Paul was talking about irrational rotation.
Yes.
It's a specific Kronecker.
Yes.
So what is that it also appears in the definition of the discrete?
Yeah, it's a rotational abelian group, but being Kakutan equivalent in the discrete time case means that we have, let's say we have X here, we have Y here, and the guys are going to be Kakutan equivalent if there exists a set of positive measures here, a set of positive measures here. We looked at the first return map. So we looked at the first return map induced here from the almost every point, the same here. And these two guys, here I'm looking to XT, here is phi S, and XT is Kakutan equivalent. Here I have a measure mu as well, measure mu. They are Kakutan equivalent if this induced maps A, first return map on A, the restriction of the measure normalized is isomorphic to B as on B, and then the rational rotation is going to be
right. So it's the rational rotation that appears on one side, not the general Kronecker system, right?
Yeah, but they're going to be Kakutan equivalent based on this notion. Based on this notion of looking to the first return map, this is going to be the same in the end.
For all of them.
Yeah. Yeah. So yeah. So well, we have the notion of the gap. We can talk about delta in the same way. And we can find rho FK. And then here, now that we know what is this object, we now know almost everything that we want. What is missing is what is this characterization. So the characterization is the same as what we have. And have a continuous form. Mu an ergodic measure. Then mu is into the Kronecker. If and only if there exists a set of full measure. Such that rho K. So yeah. So we have some nice properties about this. Here's some facts. If with respect, let me denote this. Here is the Feldman-Katok pseudometric for discrete time with respect to the time t map between x and y. So for 0, then for the flow is going to be, let me denote this way. I'll just avoid misunderstanding. This is not going to be 0. Also, let's say that we have a transformation t for which this pair of points they are 0. Then, if we look to suspension, if we look to the flow, which is a suspension, actually here special flow in the sense that Jonathan was saying, it doesn't matter what is the root function. Then we have S and Y R is up to 0. If we look to generic points, so those now in the context of flows, so in the context of flow, we have mu st of a set A as 0 to t. So this is the empirical measure. The point is generic if this X is generic for a measure mu if mu xt converges to mu in the weak side topology. So if one point is generic, 0 distance, the other point is also generic. So we recover the same facts that are proved for those guys. So we have a strong connection between the continuous time version and the discrete time version. But not always, if I have an ergodic measure, this measure not necessarily will be ergodic for all the time t maps. This is not always true. But this happens for many times. So one direction of this theorem is pretty much direct consequence of the discrete time version, which is based on what I was saying there. Let us assume that we have so first there is this classical theorem saying that if mu is ergodic for the flow, then mu is ergodic for all but countable n time t maps. So this gives us some direction. Why? Because there is another theorem also from Ornstein, Rudolph, and Weiss, where they show that. Let me write this note. Let me write this there. Here, Ornstein, Rudolph, and Weiss is that if mu is an ergodic measure for the flow, and mu is ergodic for a time t map. Then mu is losing current. The discrete time motion. So not always we have ergodicity. It doesn't hold that we have ergodicity for every time t map, but if the time t map is ergodic with respect to the same measure, then being loosely Kronecker, is loosely Kronecker. If we have a measure that is loosely Kronecker, and the measure is ergodic for the time t map, then this is going to be loosely Kronecker for this time t map. So one direction now becomes easy. Why? If we assume that the measure is loosely Kronecker flow, then we know that there exists a time t map which is ergodic, because except by constantly many, we're going to have it. Once we know that we have an ergodic time t map, since the measure is loosely Kronecker, using Ornstein-Rudolph advice, we know that this measure is going to be loosely Kronecker for this time t map. And using this fact, so using their theorem, we know that with respect to the time t map, there exists a set of full measure for which the points are 0 for the time t map. And using this fact, we guarantee that we have 0 distance with respect to the flow for the same set. So this direction.
Wait, that fact is the fact that if you know it for anything up.
Yeah, if for some t, for some t, if for some t we have 0 distance, then we can extend for the whole flow. Because we can partition the time, and then we can, if it's 0, we look to the good times here, right? And then we can make it be good flowing here with essentially the identity.
So continue to use.
Yeah. So yeah, we can partition the time into the time t maps, and then we are good. So well, one direction is good. The other one, which is the hardest one. And for the hardest one, what we use Ratner strategy. But okay, so how can we use something topological for making this going from the topological version to the discrete time version? This is the main question. And what we use is the following. So, the thing that I proved actually was that, okay, I erased that, but what I proved is that KT epsilon T, if we have a set of measure for which this all holds, then KT is going to be singleton. So we can find a unique pole for every partition, every T large, and every epsilon small. Okay, but again, how we pass from topological notion to a measure theoretical version? How can we say this for every partition? And here's where the more technical part of the work appears, because we don't look to all of the partitions. I proved that we can look to part of them, and there are some good partitions that we can look at, and those are called, I decided to call it epsilon essentially open partitions. So what is that? Let's U be countable basis for the topology. Okay, we can assume that this U is closed by finite unions and intersections. This is not a problem. And then we say that a partition P is U regular if at most one element, one atom, let me call atom. So this partition is P1, P1 if it's a P, doesn't matter, K. And each of these guys I call an atom. And it's going to be U regular if at most one atom is not in U. Okay. So we're going to have many guys being open, not only open, but in this contact basis. And at most one guy is not there. And if this guy is not there, to be an epsilon essentially open partition, it's actually mu epsilon. So a partition P is mu epsilon, essentially open if it is U regular and if one guy here in the partition is not, if there exists an element of the partition that is not in the family U, then the measure of this atom is less than X. Okay, so we are looking to some partitions that are very good because almost all the guys are going to be open. And if someone is not open, then it has a very small measure. So why it's good to look at that? Because we can look to a metric in this space. There's a very classical metric. Like this. So we can define a metric in the space of partitions. So if we take a partition P, P1 of P, then we can define a function on the space here that associates with the J such that X belongs to the J. Okay, it's just like you can find out where it is. Then, but this depends on the order. Usually people fix the order, but we don't need to look at that. We can define the distance between two partitions as the infimum of the set and wait. So I just said finite partition. I didn't say that they should have the same amount of atoms. If they don't have it, we can just assume that the complements are, we complete them with zero sets, empty sets. Then we can pretend that they have the same. And this infimum is taken over all possible orderings that we have. Okay? So essentially, if these two partitions they are close, then we have the space here, this is gonna be a partition here. The other one is something similar. You know, but they're somehow similar. And they don't need to have the same amount of elements, this is not a problem. But if they don't have, well, this is saying that, let's say the cardinality of Q is bigger than P, then we don't have much more. What is left has a small measure as well. So we may have more atoms, but in terms of measure, the union of these atoms is not much. And then, yeah, we have essentially, so we don't need to look to ordered partitions, and we don't need to have them with the same cardinality. And why I look to this metric? This is just a generalization of something that people usually look at, but enjoying these guys because if mu, let me denote this way, doesn't need to be invariant, just a Borel probability measure. And epsilon greater than 0. Then the epsilon essentially mu epsilon essentially open partitions are dense. So if you fix a measure and you fix epsilon, then the essentially open partitions, they are dense. And this is not hard to see, right? Because as I said, there is an easier way to prove since I'm not considering partitions with the same cardinality. So we all know that we can take for each atom a compact set which has almost the same size. In a certain way that what is left already has small measure. Then from these, we take someone in U to make it regular.
Even though I don't think it's necessarily inside.
Sorry? Yeah, I mean, this drawing is a little bit.
It's okay. You use regularity. It's okay.
We use regularity, but yeah, they could be weird. But the point is, we can have compact sets inside.
No, because it's going like it's inside the original.
No, yes, it looks like that, but it's not. They are not necessarily inside the initial one. So yeah, they could be somehow. Yeah, that's true. This is somehow cheating. Could be like that.
Oh yeah, from an initial point of view. Yes.
But yeah, it's more or less
tiny places where it comes out.
Yes, right.
Yeah. Okay.
But to take out my
Yeah.
how do you call it? Titus condition.
And what happens is we can just so we look at this new partition in blue, and we add one more atom, which is the complement. And then the remainder is gonna be small. So it's gonna be epsilon essentially open partition. So okay. Sorry, I don't have much time. So finally, why we can move to these good partitions? Because then we have the most technical lemma with a lot of calculations. Let's say the following. Let me catch it here so I don't say something wrong. So 5 as well. New and ergodic measure. And 2 partitions. You don't know exactly what they are. So for every delta, there exists T0, not an H here. Actually contain the generic points. This is not super important now, but again, what matters is that mu of this guy is big, and we have ftx y q is likely to equal to 4 times ftx y q plus twice the distance between the partitions plus delta for every t bigger and x, y in this stage. But here's the technicality, is that no matter which delta we take, we can find a very big set for which we have this weird comparison. So we can estimate with respect to a partition P based on a partition Q. Yeah, it hasn't done calculations in it. It is, yeah, it's more technical. But now, since we have density of the good, so we can just look at the good ones. And if they are delta close, if the delta is small enough, here we have zero distance between these guys. So for any delta, we can have t large enough, delta close. Then we use the Lebesgue number of this cover, and we can find this thing being good. And using these good partitions, so we can prove that for good partitions, these holds. And once we prove that for good partitions these hold, we use that to show that for any partition, these holds. And then we have the theorem. And then we have the theorem. Okay, so just to finish, in the abstract, I promised to talk about topological models. And let me just finish saying a few words about topological models. What was realized is that still in the discrete time case, they define a notion called, well, so we have, if for almost every point is they have zero distance, then the measure is using Kronecker. So we can define phi to be topologically using Kronecker. If instead of looking to full set, we have this for every pair of points. It's natural. Instead of looking to me almost every point, we look to all of them. And what we have, based on what I said, but I didn't really write, that it's not really hard to see that then phi is topologically using Kronecker. Then it's uniquely ergodic. Because if a point is generic for a measure and another point has zero distance, then this other point is also generic for the same measure. So we can only have one measure. And why this is connected with topological models? Because phi is a topological model of a measure preserving flow, non-consecutive continuous, if is uniquely ergodic. So let's say that it's U. So we just have one invariant measure, and x by mu is isomorphic to y. So it's a topological model if it's uniquely ergodic, and it's isomorphic. When we look to this unique invariant measure, this is isomorphic to the initial system that we have. But from the topological viewpoint, topological models can have a very, very different behavior. Because we are looking to where the measure is concentrated. We don't know what is happening outside this. But what we actually have is that phi is a topological model of Bernoulli Kronecker of this, right? It's faster. Bernoulli Kronecker, magnet preserving flow, if and only if phi is topological illusory drive. So one direction is easy. If it's topological illusory Kronecker, then we know it's uniquely ergodic. For every point we have zero distance, then for me almost every point we have zero distance, then the measure is illusory Kronecker. Good. Now we take a topological model of a illusory Kronecker measure preserving flow. And what happens is that there is another theorem similar to this one that says that this guy is uniquely ergodic. Then if it's uniquely ergodic, then for all but completely many, it is going to be uniquely ergodic as well, the time t map. And this theorem was also proved in the context of discrete time systems. So the same theorem was proved in the context of discrete time systems. So the time t map is a topological model of a illusory Kronecker map. By the discrete time version, the Feldman-Katok distance is 0 for any pair of points. And using these again, we have zero distance for everyone. And then we have that topological illusory Kronecker. So in summary, what we have now is that we know a common behavior between all topological models from a topological perspective of a illusory Kronecker measure preserving flow, actually for any illusory Kronecker measure preserving flow. So they share this common behavior. We don't know about other kind of things, but for sure, at least these nice and well-structured behavior holds for all of them. Yeah, so in particular, we have that if we have a suspension, just to finish, just some few comments. If we have a suspension or special flow over a topological illusory Kronecker map, this is going to be topological illusory Kronecker. But on the other hand, we could have times for which the time t map is not ergodic. And if the time t map is not ergodic, then we may have a topological illusory Kronecker flow for which, for some t, but not more than completely many, they are not necessarily topological illusory Kronecker. Unless the guys weakly mix in the sense of measure theory, but I don't really want to get into that. Thank you.
Are there any questions? I have a question. Very interesting on that. So you said your starting point was that there were the results for the Z systems, right? For the discrete.
Yes.
What about if somebody tried also to go to other discrete, let's say ZK, and so on?
This is one of my plans, actually. Going to ZK and actually even RK. What is the main problem that we have here? If you notice, the whole time I was talking about being increasing this monotonicity is important. For n delta matching, I'm looking to monotonicity. For the T delta matching, TS on delta matching, we are looking to monotonicity. So if we go to higher dimensioning, then we don't really have this monotonicity. But there are some works where people studied illusory Kronecker actions, RD and ZT actions, where they look to the grid and a great portion of this grid, but they didn't really have enough time to look at that. But they have something which is similar to the notion of matching that Ratner had, but for these other kind of actions. But then, yeah, I still need to check whether we could still have the same results. And in the context of especially RK actions, this makes even more sense because any pair of RK actions, they are orbit equivalent once we go to more dimension. So it makes even more sense to talk about this control orbit equivalence. But yeah, both for ZT and RD, yeah, it's as far as I know, it's not yet done. but it's something that I am interested in. Just didn't really have much time to look at that.
There is also this famous output, I think it's called ergodic without the past.
Sorry?
There is this famous output called, I think, ergodic without the past. And this is motivated by the fact that when you pass from said more general groups, you lose the past and future.
Yeah.
In that sense, and then I don't know what if they did with these kinds of questions, but maybe it can use
Maybe. We don't know about this word.
I think this was for certainly Weiss is one of the core of those, but entropy without that. Who wrote it? Plus. And plus the plus. Only plus now? No, then you open this. Plus to Bernoulli. Glasner Weiss and to Bernoulli.
Okay. Good to know. Good to know. This may be useful as well. Because yeah, the big problem.
You know, because this is not the only place for such a problem.
Exactly, of course not. The question is whether we can look to these different directions and we still have this proximity. But yeah, this is an interesting direction to go.
All right, so thank you very much.
No, kind of a philosophical question.
Yeah.
So in this sort of result, or even the characterization of the losing Kronecker, like which direction is the important one? In a sense that, like, how to think about it? Is it a way of saying, okay, if you are losing Kronecker, then you have this nice strong property, and this is what you then use? Or is it in the other direction? You want to check that the system is losing Kronecker, and you get a criterion which is easier to verify, or maybe both.
Yeah, I mean, both of them, they will have some implications. For instance, this shows, for example, that the horocycle flow, since we know that this is uniquely ergodic and loosely Kronecker, then it's topologically loosely Kronecker. So we have this other direction.
Stronger.
So yeah, we get some extra information about the topological viewpoint of this flow. So that depends. I mean, this is a way of characterizing. So this is what was missing. And yeah, and then, well, maybe you can look to some parts of the system, not necessarily the whole thing, and try to go to the whole thing. It's a way of finding out if the system, if a measure is loosely Kronecker or not, and find some zero entry. So one of the good things about being loosely Kronecker, I think the main application of loosely Kronecker measures usually is to prove that certain measures they have zero entry. So if you don't know exactly, this is a way of identifying if a measure has zero entry, because loosely Kronecker we have zero entry. And this was how they proved at first that this GIKN measures they have zero entry. They proved that they are loosely Kronecker. In particular, they must have zero entry. Both directions they are in the end somehow relevant.
Thanks.
Any other questions? Okay, if not, let's thank this.